One of the earliest users of lifts was the mining industry. And in this program, we're going to be looking at lift design. In particular, coal mining lifts, like this one at Ellington Colliery in Northumberland. And we're going to do this for two reasons. First, to look at some of the applications of the engineering mechanics principles which you've studied in the course. And secondly, to get a taste of the complex and creative process that is engineering design. The characteristic gantries seen at coal mines are part of the traditional mine hoisting system. But in addition, here at Ellington, there's a pilot scheme which uses a conventional lift system that you might find in any tall building. And later we'll be examining some of the design problems involved there. But first we'll look at the more traditional system which hoisted the cage I came up in. The size of the elements is the first most staggering part of the design. It wasn't that long ago that you would have found similar systems driven by steam. Nevertheless, the engineering mechanics principles involved are as valid today as ever. The system is a well-established design. So, what are those principles? Well, in the winding house, this huge drum acts like a simple winch to hoist the rope. But what determines the size of the drum? Well, for a start, it has to be of a large enough diameter so that the rope doesn't suffer too much bending as it's wrapped around the drum. And the theory of bending gives us a way of calculating what the maximum curvature is that the rope can take before it reaches its strength limits. And in mining practice, they use a ratio of drum diameter to rope diameter of 120 to 1, which is well above the safe condition by a factor of safety of 10. Well, the rope itself has a number of features which increase its capabilities. If we look at a section, we'll see that it's made up of a number of thin steel strands, which means that it's more flexible in bending than an equivalent solid steel rope. Also, the strands themselves are twisted around the rope so that as the rope winds onto the drum, any part of a strand will be first on the bottom, close to the drum where it will be in compression, and then on the top, away from the drum, where it will be in tension, thus evening out the stresses on any single strand. Well, as well as resisting bending stresses, the rope also has to take the cage and the men. After all, that's what the lift system is designed for, to take so many miners over a certain distance in a given time. So let's take a look at the whole cycle of lift operations. During the cycle, the cage undergoes acceleration, constant velocity motion, and retardation in one direction or another. During a cycle of operations, the forces on the cage and the rope vary. A dynamic analysis of one part of the cycle will show this. At this part of the cycle, the cage and miners are moving upwards with an acceleration A. The free body diagram is the first step in the analysis. The cage and the miners together have a mass m, so the weight is mg. And the force exerted by the rope on the cage is F. Taking upwards as the positive direction, we can now write down the equation of motion. F minus mg, that's the forces on the cage, equals ma, the mass times the acceleration. That comes from Newton's second law, and this gives an expression for F. F is m multiplied by g plus a. This is an expression for the force exerted by the rope on the cage
for an acceleration a upwards. Now that acceleration a upwards gives the maximum magnitude for F. But if a is downwards, then it takes a negative value. This gives the minimum value for F. When the cage is moving with constant velocity, or when it's stationary, there is no acceleration. With a 0, F is simply mg. So the loading on the cage and the kinematics of the lift determines the maximum tensile load on the rope. This information determines the diameter of the rope required, and in turn the rope size will determine the minimum drum diameter to allow for rope bending. The drum itself carries not one but two ropes, counter-wrapped, so that while one is wrapping, the other is unwrapping. This means when one cage goes up, the other goes down. Running two cages from a single drum reduces the torque that has to be supplied to the drum. Suppose F1 is the tension on one rope and F2 on the other, and the drum is of radius r. Well, taking moments about the centre of the drum, with anti-clockwise being our positive sense, then the moment of F1 about the centre is F1r, and of F2 about the centre is minus F2r. If T is the torque applied to the drum, then the sum of the three turning moments must be equal to I alpha. I is the effective moment of inertia of the drum, and alpha is its angular acceleration. From this equation, you can see that the required torque, T, is in fact dependent on the difference between the tensions in the two ropes. This torque is in fact supplied from a 260 kilowatt motor via an 8-to-1 gearbox and finally to the drum itself. The whole system incorporates many safety features. For example, this gauge monitors the position of the cages, and these centrifugal governors monitor the speeds. Should the cages run too fast, the governor will trip the brakes. Under normal conditions, braking is in two stages. First, the motor drive is slowed down electrically, and finally, mechanical brakes are applied.
So, we've looked at various factors which determine cage loading, rope and drum size, motor power and lift kinematics. But there is one final point. You see, the length of rope wound around the drum corresponds to the depth of the mine shaft. The deeper the mine, the wider the drum has to be in order to take the extra wrap. Well, in this mine, the mine shaft is 150 meters deep, and already the drum is quite wide. So you'll find that in very deep mine shafts, a different drive system is sometimes used, a friction or a traction drive.
The traction system has a continuous rope between the car, seen here on the left, and a counterweight on the right. Unlike the drum system, the rope doesn't need to be stored. The rope is just hung over the sheaves. It's the friction between the traction sheave and the rope that provides the required traction. Moreover, if the counterweight bottoms, the traction sheave slips, so the car can't be drawn over the top, a useful safety feature. Well, the traction system installed here at Ellington has been designed to carry about 20 miners at a time, to move a shift of 300 miners in half an hour. A traction lift system of this sort hadn't been installed in a coalboard location before. In principle, it's a conventional lift inserted into a coal mine shaft. So what were the problems involved in the design and installation of such a lift? Harry Pettinger is technical director of the company involved in this installation, and I asked him why such a system hadn't been used before, and why was it that they had decided now to pilot such a scheme.
Well, up till just recently, the coal board have been mainly concerned with hoisting coal and materials, and the lift industry, on the other hand, is essentially concerned with lifting people. The coal board has therefore developed a quite different philosophy to that which we use in the lift industry, and it was only as a result of the National Committee for the man riding in mines that we were invited to install a conventional lift into a mine shaft.
What about the particular problems at Ellington Colliery?
At Ellington, we were presented with an existing circular mine shaft of approximately 4.5 meters in diameter. We then were able to put in a car of maximum size, which by agreement with the coal board resulted in a car which takes 20 miners complete with their equipment. It was also agreed with the coal board that suitable speed would be 5 meters per second, which would give a reasonable flight time from top to the bottom of the pit.
This proposed motion includes certain assumptions about the kinematics. To get a better picture of what's happening, we'll look at the motion curves for a complete cycle. First, the displacement time curve. This includes a loading time, the ascent time, unloading, and descent. From the displacement curve, we get the velocity profile. Positive values in ascent, negative in descent, with periods of constant velocity motion. And from the velocity profile, the acceleration time graph shows positive and negative values. In practice, however, the acceleration graph would look a bit more like this. Have a look at what the velocity profile would look like with this changed acceleration requirement. You can see that the effect is to round off the corners, giving a smoother ride to the passengers. Have a look at that again. This is the sort of velocity profile we'd aim for in practice. So with the lift motion and the loading established, you're then able to go ahead and choose a machine to do the job.
Yes, in this case we decided to use a perfectly standard, if large, standard machine used in the lift industry, and to employ this in a coal mining environment, but also to incorporate all of the safety devices we would normally incorporate on a lift installation. Now, these safety devices are spelled out in considerable detail in British Standard 2655, General Requirements for Electric Lifts. This specification requires a minimum ratio between rope diameter and sheave diameter of 40:1. In the case of this machine, the sheave diameter was 910 millimeters, and we decided to use a rope of 16 millimeter in diameter. And thus you will see we achieved a rope sheave diameter of about 52:1, well in excess of the 40:1 required in this specification.
Well, we have a sample of the rope here, a 16 millimeter rope. And if we compare it to the rope you saw in the drum drive system, we see immediately that it's much more flexible, although it does have a similar lay. The same principles of bending and tensile loading apply in this case as well, of course.
Yes.
One thing that interests me, though, is that you said that your ratio of drum to rope diameter was 40:1, whereas in the drum drive system, in the mines, they use 120:1. Now, why is there this difference between your specifications and the drum drive system?
Well, you have to remember that in the drum drive system, they use a single rope, which is very much larger in diameter than that, and is a very much stiffer rope, as you saw,
Yes,
I think,
yes.
from flexing the rope as compared with that one. We use a very flexible rope, such as you see there, and we use several ropes. In this case, we decided to use 8 ropes.
Yes, yes.
It's for this means that we can get down to a safe ratio of 40 to 1.
Yes.
So we've established the total system load, including the rope weights. What's the next step?
Well, we know the amount of traction that we require to move the system, and we have to make sure that we have sufficient traction between the rope and the sheave to drive the whole system. Please remember that we're relying upon friction between the sheave and the rope to effect the drive.
So, how do we relate friction and traction? Well, the ratio between the tensions, T1 and T2, is given by the equation T1 over T2 equals e to the mu theta, where theta is the angle of contact between the rope and the sheave, and mu is the coefficient of friction. Well, there's little that can be done about mu for a given pair of materials, so the only way in which the available traction could be increased would be to increase theta. But there's a limit. An alternative is to allow the rope on the right to wrap once around the idler pulley before being wrapped a second time on the traction sheave. This then gives an angle theta equal to the sum of the two contact angles between the rope and the sheave, thus increasing the traction. This is called a double wrap drive.
Yes, we had to use a double wrap system in this case to achieve the necessary traction. We were using 8 ropes to suspend the load, and 8 ropes double wrap gave us the necessary traction. The simple theory of e to the mu theta doesn't exactly apply in this case, because we have to take into account the shape of the grooves and several other factors that we have found by experience. Another problem that your students may be interested in from the mechanical design point of view is the construction of the car frame itself. This is subjected to a whole series of different loadings.
The normal structure of a lift car is of a box-type arrangement, contained within a frame. The base of the frame supports a platform which carries the passengers. The platform effectively spreads the load, so that the cross-member supporting it is in effect a beam under a uniformly distributed load. So this beam has to be designed for stresses resulting from downward bending. The top cross-member, on the other hand, experiences effectively an upward point load at the centre due to the ropes. So this beam has to be designed for bending due to a point load upwards. And the side members, under normal operation, are under tensile loading. So this is the normal loading condition of the car frame in normal flight. 2 beams and 2 members under tensile loading. But as with the drum system, there are certain safety features, and these in turn are going to affect the forces in the car frame. The car itself runs on guide rails. The guide shoes on the car keep the path of the car in line. Should the car approach too close to the base of the shaft, a buffer will absorb the kinetic energy of the car, and under these circumstances, the base beam undergoes bending upwards. The buffer itself, one's under test at assembly here, absorbs the car's kinetic energy by means of a hydraulically damped piston in compression. However, the buffer will only absorb kinetic energy at about normal running speed. Overspeed is monitored by a centrifugal governor. In principle, it's the same kind of device as used with the drum system. 2 flyweights here and here move away from the center of rotation against a spring. And at extreme overspeed conditions, they trip the safety device, that locks the car against the guide rails. This emergency might arise if, for example, the ropes were to snap. The car comes safely to rest. Without the emergency devices, the car would continue in free fall, and the buffers couldn't possibly absorb the energy of that fall. Well, the emergency stopping devices themselves are usually mounted below the car. So now the side members would experience compression, and then should be considered as struts under shock loading. Whereas previously they were considered as tensile members, they now need to be modelled as struts. And in general, the whole system, car frame, ropes, and winding machinery, have to be designed for these different sorts of loading.
Well, here's the final version of the traction lift system they designed. And we've taken down the guardrail so we can get a closer look. As you'll notice, there are 16 ropes on the winding sheath. That means 8 ropes in double wrap around an idler pulley down below. And if you remember, that's what the designers calculated to give enough traction to the system. Well, during testing of the machine, several different lift speed profiles were measured. And I have here a typical graph showing the car velocity against the distance of car travel. And you can see the acceleration period, constant velocity lift, and the deceleration period. And the profiles are smooth, so there aren't any sudden changes of velocity which could cause discomfort to the passengers. So, there you are, a brief glimpse at some of the features of lift design. Now, we've looked at 2 designs, the drum drive and the traction drive. And you've also seen how some of the theory, which you've studied in the course, has been applied in a practical engineering situation. And as far as engineering mechanics is concerned, that's the ultimate goal of our study, understanding the basic principles by which machines and structures are designed.